Hi, Trig students. This is the rest of your Chapter 9 packet. We're going to start with number 7 and we are going to finish. So this is our very last video that we're going to have for the class. Well, other than our test 4 review. I won't leave you hanging for that. We are going to have a test 4 review, but this is the last piece of new material that you're going to have. So we're going to finish this. Now, all we have left to cover is we have what happens with hypothesis testing when sigma is unknown. That's what we're going to start with number 7. And we also have what to do with proportions. So remember, what you're going to need in front of you is your packet, if possible. Otherwise, you can just follow along. You are going to need this little handy dandy reference sheet that's on content that kind of gives you each possible scenario, and we're going to start with this side that says if sigma is unknown. And last but not least, you're going to need your t-chart. Now I know we haven't used this since chapter 8, but you are going to need that t-chart that discusses the degrees of freedom and the area and the right tail. You're going to need that for the situation where sigma is unknown, the one that we're about to start. Okay, and then also your graphing calculator. All right, we're going to jump right in then. So, number 7, let's read this and see if we can figure out exactly what type this is, and then we'll follow along with our steps. So, consider, here's our null. HO is mu equals 80 versus H1, there's our alternative, mu does not equal 80. Okay, so what kind of test are we looking at here with the does not equal? That is a two-tailed test. Okay, so that's what we're looking at. We're going to go ahead and draw that. We're looking at a two-tailed test here. Okay, that is normally distributed. All right, now here's the nitty-gritty. We have a random sample of 25 observations taken from this population, produced a sample mean. Well, we know a sample mean is X bar of 88 and a standard deviation of 6.2. All right, this is when you're really going to have to read the question. If you are skimming the sentences, looking for numbers and keywords, you are going to get confused because I see the word population and I see the word standard deviation, which may lead me to think this number is sigma. I would be wrong. This is not sigma. Let's read that whole sentence again. We're discussing a sample, okay, taken from the population. So we're talking about a sample here. It gave us a sample mean and a standard deviation of 6.2. That is S is 6.2. This means sigma is unknown. We don't know sigma. We do not have a population standard deviation. Sigma is unknown, okay? What we have here is simply S. So we have to be very careful on that. Sigma is unknown. I'm sorry that ran off the side there. I'll be more careful. Okay, then it gives us alpha. And then it says, would you reject the null? That's all it says. Okay, well, if I take my little handy dandy reference sheet over to sigma is unknown, remember I have two approaches. I have the p-value approach. This is your probability value approach, or the critical value approach. Well, I don't know which one to use because it didn't tell me. This is an instance where you get to choose. Now, I will tell you, you are going to have a lot of opportunities to practice the p-value approach for sigma is unknown. So I am going to do the critical value approach here, okay? Simply because I know what's coming up and I know we have a lot of these. So I'm going to do this one. But before we jump right in, let's just look over this page for a moment. So being that we don't have sigma, notice what I'm looking at here. I'm not looking at sigma of X bar. I'm looking at S of X bar. Okay, S divided by square root of N. I'm also looking at my degree of freedom. And I'm also looking at, rather than Z observed or my test statistic, I'm looking at T observed. That's my test statistic. Here's my formula for that. X bar minus mu, remember that's right from your null, divided by this value over here. Okay. Now, basically, the steps for the critical value approach are extremely similar. We are still following sort of the same idea, except that we're going to be using our t-chart. The p-value approach is when it gets different. P-values for sigma unknown are a range. Okay, you're going to have a smaller value and a larger value. So now we have a range of p-values. Then we're going to compare our significance level. If it is larger than the largest p-value, if it's so significant that it's larger than that largest p-value, then we reject, okay? Otherwise, we fail to reject, all right? So that is the largest difference there, the biggest difference. Okay, well, we said we're gonna go critical value approach, all right? And again, I'm only doing that because, well, I get to choose, and because I know I'm gonna have a lot of p-value practice coming up. Okay, so since I'm doing critical value, I'm gonna make some regions. I'm gonna have two critical values here, a negative and a positive. And this is gonna be my non-rejection region. These are my rejection regions. I also know that these are my alphas when added together. So if I take alpha divided by 2, since I have 2 of them, I'm looking at an area here of 0.005, just like that, okay? All right, so now what I'm gonna do is follow my steps. So I'm gonna go back to my little paper. My first step, find T observed from the above formula. Okay, so I'm gonna use both of these guys and I'm gonna find my T observed. So still called a test statistic sometimes, but it's not Z observed anymore, it's T observed because sigma is unknown. Okay, so S of X bar is gonna be S, that's S, divided by the square root of N. So divided by the square root of 25. I'm going to take that out 4 decimal places if I can. Unfortunately, I can't. It just gives me 1.24. That's it. Okay, we're going to do our T observed. That's going to be X bar minus mu. Remember, don't panic if you can't find mu. Where do I go? To the null. He's up here with the null. Divided by S of X bar. My T observed comes out to be 6.45. That is a large T observed. Okay, now I need my 2 T criticals. Okay, I'm gonna follow my steps. I find T critical from the T chart using alpha as the area and using the degrees of freedom. If I have a two-tailed test, divide alpha by 2 first. Well, I already did this part. Remember, I already did that part. So here's what I'm looking for, okay? The area I'm looking for is 0.005. I already divided my alpha by 2 because I have the 2 regions. What's my degree of freedom gonna be? 25 minus 1. So 24. Okay, so here we go. Here's my T chart. I go down here to degree of freedom is 24, and I'm reading across of 0.005. Come straight down, and I'm looking at 2.797. 2.797. Okay, so remember, that's the positive, and here's the negative. So I have 2 of those guys. All right. Now, all I have left to do is compare. So I have my critical values, I have my observed value. Now I'm going to check and see if T observed is in the rejection region or the non-rejection region. So I guess I should put that I found my critical values. You don't have to do this, but I just want to make sure you have all the information. Okay, so I made one negative and I kept one positive. Oh, I put an extra decimal in there. Okay. All right, now we're going to see where it falls. So here we go. I'm going to take 6.45. Here's my 0. And 6.45, I told you that was a big T observed. It is way on in the tail, right? Like way on over here. So we are definitely in the rejection region. Okay, for absolutely sure. So 6.45 is in a rejection region. That means, okay, would you reject the null? Yes. Reject the null. And there we go. Okay, so a little bit different. Finding your T observed is very, very similar. The difference is the critical values. We did not go to inverse norm. We went to our T chart. We used degrees of freedom, and we used our alpha, which we had to divide by 2 because it was a two-tailed test. And then because there were 2 of these, we made one negative and kept one positive. If there's not 2, we don't have to divide by 2, and we don't have to make one negative or positive. We just take the 1. Okay, there we go for number 7. All right, let's look at number 8. Number 8 is tricky. Again, this is right off of Wiley, but the wording is a little bit tricky. It's hard to determine what is the null and what is the alternative. So that's why I like to do this one together. Okay, let's read it. So, the president of a university claims that the mean time spent partying by all students, so we're talking about a mu, at this university is not more than 7 hours a week. Okay, so every year they put out these lists. I don't know who puts them out, to be honest with you, but there's always a list put out of the top 10 party schools in America. And so some universities love to be on the list. They like to think of themselves as a party school where they just party all the time. And some universities, they don't want that reputation. And so they try very hard to not be on that list. So I'm thinking that whatever university this is, the president is saying, no, 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 not us. So he's claiming that his students they don't party more than 7 hours a week, not more than, okay? All right, so we'll come back to that in a minute. That makes it really difficult to see, is that the null or is that the alternative? So we'll be back. A random sample of 40, okay, well, I know that's in, taken from this university, showed that they spent an average of 9.8 hours. Okay, so we're talking about the sample. If that sentence starts off talking about the sample, everything in the sentence refers to the sample. So that's the sample mean, okay? They spent an average of 9.8 hours partying the previous week with a standard deviation of 2.3 hours. Now again, if you're just skimming, how are you going to know if that's sigma or if that's S? You're going to have to read the words. And so if you notice, this is all in the sentence describing the sample, okay? That means this is S. That's your sample standard deviation. Sigma is unknown. It's such a slight little, just a hint of what kind of problem it is. You have to really be on your toes to catch it, okay? All right, test at the 2.5% significance level, all right? Well, alpha is your significance level. We don't want a percentage, so we're gonna divide by 100 and get 0.025, okay? It wants us to test whether the president's claim is true. So, if this is what they want you to test, they want you to test the president's claim, then that would be the alternative because that's what drives the test. So as we go through to make our null and we go through to make our alternative, okay, the president's claim is what we're testing. That's the alternative. So let's go back and see what his claim was, okay? His claim is that the mean time spent partying by all students at this university is not more than 7 hours per week. Well, how do I write not more than? Well, that's another way, a weird way of saying less than, right? Less than, which means that the null is going to be equal to this number. So that's a really sort of a tricky null and alternative. So you want to be careful there, okay? This is what we're testing. It's our alternative. Another way of saying not more than is less than, and then your null is always equal to. So there we go. This is what we're testing. What kind of test is a less than? That is a left tail test. That's what we're doing. All right. Okay. So now it also, again, just like number 7, does not mention critical value or p-value. So we get to choose. All right. I'm choosing critical value again. Now, the reason I'm doing that is because you are going to have plenty of p-value practice. It's going to start with number 9. It's going to continue through the rest of these sigma unknowns. So this is really our last chance to do a critical value sigma unknown. So we're going to go for it. Okay, we're going to do a critical value approach. All right, I don't know why I put a D on there. Critical value approach. All right, so let's make a picture. Here we go. We're going to have a left-tailed test. We're going to have a critical value here. We're going to want a negative critical value since it's a left-tailed test. This is our non-rejection region. This is rejection. Since it's critical value, this is alpha. That happens to be 0.025. All right. So now we're going to hit our little reference sheet here. Okay. Critical value approach, we want to find T observed from these formulas. All right, here we go. First thing we're going to do, S of x bar. That's going to be S divided by square root of n. We're going to go out 4 decimal places, 0.3637. Then we're going to get a T observed. That's going to be x bar minus mu. Remember, mu is your null. Okay, divided by S of x bar. Okay, and we come up with a T observed of 7.699. Ooh, another really big one. Okay, so you can probably at this point already tell what's going to happen. A T observed of 7.69, it doesn't matter what our critical value is, we are way the heck down here in the non-rejection range. Okay, but let's continue through. All right, here we go. Step 2 in our little reference sheet. Find T critical from the T chart using alpha as the area and the degrees of freedom. I don't have a two-tailed test, so I'm not dividing. Okay. All right, so alpha is 0.025, that's my area. Degrees of freedom, n minus 1, so 40 minus 1, I'm looking at 39. All right, let's see what we come up with for a critical value. And remember, because it's a left-tailed test, I should have a negative. Okay, it's not going to appear negative on the T chart, but I'm going to make it negative because it's a left-tailed test. All right, so here we go. If I'm looking for degrees of freedom on the first page, I am not going to find it, right? Because it only goes to 37. I have to flip it over. And I'm looking for 39. There we go. Now, remember, in Chapter 8, I already went through and I labeled this other side of my T chart so that I wouldn't mess up my columns here. So my area was 0.025, so we're looking at the third column, and I see 2.023. 2.023. Now remember, we're going to make that negative 2.023 because it's a left-tailed test. negative 2.023. All right, move that 0 out of the way. You get the idea. All right, so now we need to decide. Okay, we have our picture. Let's check and see, is T observed in the rejection range or the non-rejection range? Well, we already figured out where it was because it's so big and positive that it's way down here. Okay, so our word T observed is in the non-rejection range. Now here's where it gets complicated. What does that mean for the president's claim? What does that mean for his claim? This is his claim, okay? This is the president's claim. He claims that his students do not party more than 7 hours a week, that they party less than 7 hours a week. That's his claim. So if this is the non-rejection range, this is talking about the null, okay? So what are we going to do about the null? We are not going to reject it. It's in the non-rejection. So we are going to fail to reject the null, which is kind of like accepting the null, which means the president's claim is false. Okay, if his claim was true, we would reject the null. But because we have failed to reject the null, his claim is false. So this is probably the answer, rather than this, that my math lab is going to want. Okay, we're going to fail to reject. All right, let's look at number 9. Okay, scoot it up because number 9's a doozy. All right, here's where the fun starts. So for 9, 10, 11, 12, 13, 14, okay, and then one on the back, they want us to do both types of test. That's right, both types of test. I told you were going to get super good at this. Okay, let's read it. So we have a random sample of 18 observations, okay, taken from a normally distributed population. Now we're talking about the sample here. It produced a sample mean, that's X bar, of 42.4 and a standard deviation of 8. What is 8? That's S. So again, sigma is unknown. You have to make sure that you understand that you can have a sample standard deviation and a population standard deviation. So if we're talking about the sample mean, then the standard deviation is also going to be the sample, okay? All right, find the range of the p-value. Remember, we talked about the fact that the p-value is a range for sigma unknown, and the critical and observed values of t. So they want us to find both approaches, okay? And here's your significance level. All right. Now, they were nice enough to give us the null and the alternative. The alternative is a not equal to, which indicates we have a two-tailed test. Okay, well, no matter what approach we are looking for, okay, no matter which approach, and we're going to have to do both, number 1 in each approach is exactly the same. See that? We have to find the observed value no matter what. So let's go ahead and do that. Okay, so S of X bar is going to be S divided by the square root of n. That's going to give me 1.8856. Okay, and my T observed, remember that's also called the test statistic if you are looking in Wiley, okay, it's going to be X bar minus mu, we got to come over here to the null, over S of X bar. And I get a T observed value of negative 1.909. Oh, sorry guys. Negative 1.909. There we go. Okay, maybe what I'll do is I'll leave it like this, but I'll come down here and I'll write it over. Negative 1.909. There we go. Okay. All right, let's just draw a line there so we don't get confused now. Okay. All right, so this asked for the range of the p-value, okay, and the critical and observed values for t. Well, here's my observed value, so I've done that part, okay. Let's find the range of the p-value. All right, so we're gonna go back to our little reference sheet. We've already calculated t observed. Now I need the degrees of freedom. Okay, well, I should have probably just done that up here. Degrees of freedom are 18 minus 1, that's 17. Okay, so degrees of freedom are 17. Step 3, using the degrees of freedom, find the correct row on the t-chart. All right, 17 degrees of freedom. Here we go. There's the correct row on the t-chart. Okay, next. Okay. Go up. Okay, now locate the two t values that your t observed falls between. All right, my t observed was negative 1.909. We're going to make it positive, but we're going to look for 1.909. Okay, so on here, 1.909 would fall right between these two numbers, right? 1.909 would fall between these two columns here, okay? All right. Now go up the two columns and find the two area values at the top of the two columns. These two area values are your p-value range. Put the smallest value first, okay? Be sure to multiply them by 2 if it's a two-tailed test. So we do have a two-tailed test. We're gonna have to do that. So here we go. Here's what we did. We got our degrees of freedom. We found the correct row. We found our t observed, we made it positive, and we found the two columns it fell between. Now we're gonna go up there, and here's my p-value range. My p-value range is gonna be between 0.05 and 0.025. Now we have to put the smallest value first. The smallest value is this one. You're gonna have to switch them. Unfortunately, this goes from largest to smallest instead of the other way around. So switch those. So I'm gonna take, okay, my 0.025 and my 0.05. But since it's a two-tailed test, I'm gonna have to multiply by 2, okay? So 0.025 times 2 is 0.05. 0.05 times 2, 0.01. So what I did is I multiplied the whole thing by 2. These are my p-value ranges. That's how I found them, okay? So I went to my t-chart, degrees of freedom. I went over until I found two columns where my t observed fell between them. I went straight up. Those two areas at the top, those are my p-value range, smallest to largest, okay? Smallest to largest. Then, because it was a two-tailed test, I had to multiply it by 2. Otherwise, if it was a left-tailed test, I just leave it. Or a right-tailed test, I just leave it. But I had to multiply by 2. So there we go. So I found my p-value range. I found my observed values. Now all I have to do is find my critical values. Okay, now while we're here, why don't we go ahead and finish the p-value approach? and just see what would happen. Okay, let's just see what would happen. Whoops. So I already found my p-value range. Now I look at alpha. If alpha is larger than the largest p-value, then I'm going to reject the null. Okay? If it's largest than the largest p-value, I'm going to reject the null. Well, it just so happens alpha is 0.01. Okay? This is not larger than 0.10. So, since 0.01 is not larger than 0.10, I'm going to fail to reject. Now I know it didn't ask me that, but I'm just throwing it in there, okay? So I compare my significance level to my largest p-value. If it's bigger, I reject. If it's smaller, I fail to reject. There we go. It's not significant enough for us to reject the null. Okay, let's look at critical value. All right, we already found t observed. Now we're going to find t critical. We're going to use alpha and the degrees of freedom. If it's a two-tailed test, divide alpha by 2 first. So big difference here, okay? We're going to multiply the values by 2 if it's a two-tailed test on the p-value. We're going to divide alpha by 2 if it's a two-tailed test for critical value. So multiply by 2 for p-value, divide by 2 for critical value. All right. So it is a two-tailed test here. So here's my non-rejection region. I need 2 critical values, a negative and a positive. Here's going to be my alpha, but I have to divide it by 2, which is going to give me 0.005. Okay, so my t criticals are going to come from the t chart. I'm going to use degrees of freedom 17, and I'm going to use an area of 0.005. Okay, so I go back to my t chart. I'm looking at 17.005. Okay, here's my 17.005. Here's my critical values, 2.898. 1 positive, 1 negative. Okay, so negative 2.898, positive 2.898. Okay, those are my critical values. All right, now if I was using the critical value approach, I put those in here. I would take my t observed. Where does t observed fall? Where does negative 1.909 fall? Right in here, right? Which is a non-rejection region. So we're going to fail to reject. Negative 1.909 is in the non-rejection region. So you can see that no matter which approach you take, you should get exactly the same result, right? Exactly the same result. So this problem wanted a lot. T observed, you find first because you're going to need it for both approaches. Find your p-value. Find your critical values. Then if you wanted to follow through with both approaches, you could, just to make sure that in fact they do give you the same end answer. Okay. All right, that was tricky because it was that two-tailed test. For the p-value, we multiply these areas by 2. For the critical value, we divide alpha by 2 first before we get our criticals. All right, let's move on to number 10. Here we go. Okay, you can tell it came right off of Wiley because you have all these drop-down boxes. Here we go. A random sample of 26 observations. Okay, so we know that's N. Taken from a population that is normally distributed. Remember, this is just telling us we're allowed to use these formulas. Don't get hung up on that. Produced a sample mean, it's X bar, of 58.5 and a standard deviation of 7.5. But that is your sample standard deviation. That's your S. It all comes from this sample. Now it wants you to find the range for the p-value. Well, being that it said range, we already know then, sigma unknown, it's the only one that produces a range. Also, we see t's over here. Okay, the only time you use t is when sigma is unknown. And the critical and observed values for t. Okay, so we're using both approaches again. For the following test of hypothesis, using alpha 0.01. Okay, we have a null of 55 and an alternative of not equal to 55. All right, we're going to practice that two-tailed test again. Okay, so we're going to find all the same information again. Here we go. Don't worry about this weird thing right here. That's actually wants you to say the p-value range. Okay, so that's what's going to want there, p-value range. And then your critical values and then your observed value. All right, well, before we go any further, we know that we are going to need t observed. Okay, well, while we're at it, let's go ahead and find degrees of freedom. We know that's n minus 1, so we have degrees of freedom of 25. Okay. We know we're going to need an S of X bar. That's going to be 7.5 divided by the square root of n. We'll take that out to 4 decimal places. There we go. And we will find our t observed. That's going to be X bar minus mu, that's by your null, divided by S of X bar. That gives us a t observed of 2.380. And I'm going to put that right in this box. That's our t observed. Okay, let's try a p-value approach. Let's see if we can get that range. I guess it would help if I spelled it right. Okay, our p-value approach. All right, so if we go back to our handy dandy reference chart, we already have t observed. We already have degrees of freedom. We're going to find the row for degrees of freedom. We're going to find the column that contains this t observed. We're going to go straight up to the areas, and we're going to multiply them by 2 because we have a two-tailed test. So here we go. Degrees of freedom is 25. All right, that brings us right down here. Degrees of freedom is 25. I'm going to erase this. Sorry for the shaky camera, but we don't want that getting in the way. That's what I wrote last time. All right. There. Okay, here's our row of 25. Okay. All right, now our t observed was 2.380. Okay, that happens to fall right between these two numbers. It's right between those two numbers. So I'm going to go straight up, and here are my two numbers for my p-value range. Here's the smallest, here's the largest. So between 0.01 and 0.025, that's my range. Okay, so it's going to be between 0.01 and 0.025. But remember, it's a two-tailed test, so I have to multiply both of those values by 2. Okay, I've got to multiply both of those values by 2. since two-tailed test. All right, so I come up with 0.02 and 0.05. And that is my p-value range. So I actually think in Wiley, it lets you put it right up here in this little drop-down box. I just didn't have room for that up there, but there it is. Okay, now before we go on and find the critical value, let's see what would happen if we use the p-value approach. Alpha is equal to 0.01. Well, alpha is not bigger than our largest p-value range. So not larger than 0.05. Okay, since it's not larger, we are going to fail to reject. It is not significant enough to cause us to reject our null. All right, let's find our critical values. Okay, so for our critical values, we have a two-tailed test. So we're going to have two critical values. We're going to have a negative and a positive. And we have these regions. Here's our non-rejection region. So these regions are equal to alpha. And since we have two of them, we're going to have to take alpha divided by 2. It's going to give me 0.005 for each little region. So I'm going to use an area of 0.005 and the degrees of freedom of 25 because it's 26 minus 1. And I'm going to go to my t-chart. Okay. So I'm still looking at the row of 25. Not concerned with this now. That was the p-value approach. It doesn't have anything to do with critical values. Okay, my alpha, because remember I had to divide it by 2 because that's what you do with the critical value approach. I'm looking at 0.005. This is my critical value, 2.787. So negative 2.787, positive 2.787. The critical left is the negative. The critical right is the positive. There you go. All right, if we just wanted to verify this, I would now look at my t observed. This is t observed. Where does it fall in this number line? Well, it's going to fall about right here, right? That's definitely a non-rejection region. So that's in the non-rejection region. So I'm going to fail to reject. I will not reject. Okay. And that's the same answer as if I had done the p-value. All right. Okay, I know it's a lot of work, but you're getting so good at it, I can tell already. Okay, here we go. Let's look at number 11. All right. So let's see what we're dealing with here. A random sample of 25 observations taken from a population that is normally distributed. Remember, that's just part of the description. Produced a sample mean, X bar, and a standard deviation, that's S. No sigma here. Again, sigma is unknown. Okay. Find the range for the p-value and the critical and observed values for t for the following test of hypothesis, and it gives us an alpha. All right, it gives us the null, and it gives us the alternative. This time we have a greater than. We haven't had a right-tailed test. Okay, so now we're looking at a right-tailed test. Okay, so here we go. First thing we're going to do is let's go ahead and find t observed. We know we're going to need it because we're going to do both approaches. So S of X bar, whoops, I don't know why I underlined it, is going to be S divided by the square root of 25. Okay, I got 1.5 for that. And for T observed, I'm going to have X bar minus mu divided by S of X bar, and I get 2.333. Put that right into the T observed area. Okay, well, while I'm at it, let's find degrees of freedom. It's going to be 25 minus 1, 24. Okay, so that's just general information that every approach needs. Now let's look at the p-value approach. All right, we will have a range, okay? So we are going to use degrees of freedom and T observed. Okay, here we go. All right, here's my T chart. I'm going to erase my writing from before. Okay, my degrees of freedom were 24. Okay, here's 24. Okay. All right, my T observed was 2.333. Okay, so as I'm looking along here, 2.333 falls right here between these two numbers. There we go. I go straight up. Here's my p-value range. Now, do I need to divide these numbers by, or I'm sorry, do I need to multiply these numbers by 2 this time? No, I don't, because this is not a two-tailed test. So this is the answer. This is the answer. So here's the smallest, here's the largest. Just remember to switch the order, okay? So my p-value range, without having to change anything at all, whoops, I don't know why I put that other hyphen, is this. And I don't have to touch it because I don't have a two-tailed test. Okay, so I can even come up here and throw them right into this little guy. And there we go. Okay, so again, just for fun, let's see what would happen here. So my alpha is 0.01. Is that larger than my largest p-value? No, not larger. So I'm going to fail to reject the null. I'm not going to reject. All right, let's see if critical value matches that. Okay, now we're going to do the critical value approach. Okay, so remember, if you need to, you can always refer back to your little reference sheet. I know it gets confusing. We found T observed. To find T critical, we're going to use alpha as our area and the degrees of freedom. I do not have to divide by 2 because I do not have a two-tailed test. Okay, draw my little picture. I have a right-tailed test, so my rejection region is over here this time. I'm going to have one critical value. Do you think it's going to be positive or negative? Better be positive, right? And this is alpha. And since there's just one of those rejection regions, I do not have to divide it by 2. Okay, so I'm looking for an area of 0.01, and degrees of freedom are 24. Let's see what I come up with. Okay, so degrees of freedom are 24. Okay, remember, this is left over from the p-value approach. We don't need it. Don't let it confuse you. Okay, I'm looking at the area of 0.01. So I'm right here. It comes straight down, 2.492. And we're going to leave it positive because it's a right-tailed test. 2.492. And I can also put it right up here. Okay, if I were to just check and see what's going on, my T observed is 2.333. Okay, where does that fall on our number line? Well, it's about right in there, right? Non-rejection region. So I'm not rejecting, I'm going to fail to reject. And there we go, okay? All right, that is number 11. All right, let's do one more of the sigma unknown, and then we're going to get into some proportion problems, and those will go a little faster because we won't have multiple steps like this to do. The reason I want to do one more, because I know you're very good at this by now, is because I want to ask you a question. All right, let's get number 12 handled, and then let's look at our T-chart a minute. Okay, if we're looking at our T-chart and sigma's unknown, and we're supposed to be, you know, with a p-value approach, we're supposed to be finding where our T observed falls and then going up and seeing what they fall between. What if our T observed falls over here and it's greater than 0.1? What if our T observed falls over here and it's less than 0.001? What do we do then? Okay, that's where number 12 comes in, because that is usually a question on test 4. And I know it's a question on Wiley. So let's look at what happens in that situation. Okay, according to an estimate, the average debt for college graduates was $34,400 in 2010-2011. All right. Well, it just says college graduates. It gives you a year. I'm not really sure what that number is. I'm guessing that's probably a population mean, but let's keep going. A random sample of 485, well, that's definitely an N, it's a large N, showed that this year's average debt is this. So this average came from this sample, which means that's X bar. Okay. With a standard deviation of this, again, this came from that sample. All right, does the data provide significant evidence at a 5% significance level, that's our alpha, divide it by 100, to conclude that the current average is higher than? So they're asking us to test at this significance level whether the current average is higher than this number. And it wants us to use both p-value and critical value approaches and our t-table. Okay, we have to make a null and we have to make an alternative. This is what we're testing. Is this number higher than, greater than 34,400? Or is it equal to, which is the null? So this was the null. This is the alternative because that's what we're testing. And greater than indicates a right-tailed test. Okay, so that is what we're doing. We had to get it all set up. That's how we're going to set it up. All right, so sigma is unknown. All right, it's our last sigma unknown for the packet. The rest are proportion. Okay, here we go. So I'm going to find S of X bar. It's going to be S divided by square root of N. It's going to give me 243.385. And I'm going to find T observed, which gives me X bar minus mu divided by S of X bar. Okay, those are pretty large numbers, but our T observed comes out to be, okay, 14.791. All right, now this problem, all it wants is a conclusion, but it wants you to use both approaches, so I don't really need to circle this. All right, let's go ahead and find our degrees of freedom though. Our degrees of freedom, ooh, it's big. 485 minus 1, 484. That's a heck of a degree of freedom. Okay, let's do p-value approach first. Okay, for the p-value approach, remember, we're going to use 484 as our degrees of freedom. we're going to find what column does 14.791 fall into. All right, so two things that have never happened before are about to happen. We look at our chart. Okay, 484, not on that side. Let's turn it over. Whoop, look at there. We're down here at the infinity level because anything from 76 higher really just gives you the same value. Once your sample size gets that large, you don't really gain anything. Your numbers sort of stay the same. So we're way down here, okay, on this bottom row, okay. Now, our T observed is 14.791. Look at these little bitty numbers. We're looking at 14.791. Okay, well, these numbers do get bigger as they go across. 14.791 is definitely not between these two numbers. It's got to be on this side. It's got to be way over here. Okay, so if I go up to the area, and notice these areas, this is the largest, and it gets smallest as we go across. And remember, these are areas under the curve. So what would be the very, very largest area under the curve you could have? 1. What would be the very, very smallest area under the curve you could have? 0. Okay, so if your T observed value falls in between a column, perfect. You just go right up and take these given values. If your T observed value falls right here in this very first column, your two areas are right here. It doesn't tell you 1, you're going to have to know it's 1. Between 1 and 0.1. You have to switch those to the bigger, the smaller, and then the bigger. All right, if like this problem, our T observed value is all the way on the other side of the last column, we go up. Our area is between these two. So this is the largest, this is the smallest. Our p-value is between 0 and 0.001. Okay. So our p-value is between 0 and 0.001. And I do not have to multiply these by 2 because it's not a two-tailed test. Now, sometimes this is an option. Sometimes they just say, well, of course, it's got to be, greater than 0. That's silly. Sometimes they'll leave that off and just say that your p-value is less than that one side, okay? And if it was to fall over here, sometimes instead of being greater than this and less than this, it'll just say greater than 0.10, and it'll leave off the 0. But that's what your area would be, okay? All right, so both of these would be correct. You would just have to see what your multiple choice answers look like. All right, let's compare it to alpha. Alpha was 0.05. Okay, well, is 0.05 larger than this largest p-value? Yeah, that's larger than 0.001. So guess what we get to do? That is significant enough that we are going to need to reject our null. We don't get to reject the null a lot, but we are here. We're going to reject our null. That would be our conclusion, okay? Since this significance level is high enough, it's larger than this p-value. Okay, let's try it from the critical value approach. All right, for the critical value approach, we have a right-tailed test. Here's our rejection region. Here's our non-rejection region. We only have one rejection region, so this is alpha. We need a critical value. It's going to be positive because it's a right-tailed test. So we are going to look at an area equal to 0.05, and we're going to look at degrees of freedom of 484 and come up with a critical value. Okay, So we know that that 484 means we're way down here at infinity. Our area was 0.05, which is here. Bring it on down. Our critical value is 1.645. Okay, 1.645. All right, so you don't have to do any of this craziness when you're using the critical value approach. All right, let's look at where T observed falls. T observed is 14.791. Geez, that's a big T observed. Okay, so we are way out here in this tail, right? That is definitely rejection region. So this is in the rejection region. We are going to reject the null. So no matter which way we looked at it, we come with the same conclusion, right? That we do in fact need to reject. Okay, so those are your sigma unknowns. That's everything that could happen to you. Let's take the next few. I promise there's not that many. There's only 18. We're on 13. We can do it. And look at proportions. Look at here. You're back to z's. Okay. All right. So we're going to start now with proportions. So if you're using your little reference sheet, we turn back to the very, very back. Okay. This is reminding us of our central limit theorem, of what we have to make sure we can continue with these various computations, right? Okay, so we had these formulas with chapter 8, so they're not anything new. P hat, okay, that's your sample proportion, minus your population proportion, that's from your null, divided by sigma of p hat. How do we get that? Remember, that's your square root of p times q divided by n, where q is 1 minus p. Okay, let's look at these approaches real quick. What you're going to find, these approaches are exactly the same. Both of them. Exactly the same as sigma known. Exactly the same. So we are back to using our calculator at normal CDF. We are back to using our calculator at inverse norm. These are exactly the same things that we are using. Okay, so here we go. Let's read number 13. According to a New York Times CBS News poll conducted during June 24th through the 28th of 2011, 55% of the American adults polled said that owning a home is a very important part of the American dream. Okay, and then it gives you the source. Suppose this result was true for the population of all American adults in 2011. Okay, so that means P is equal to 0.55. That's your population proportion. Okay, all right. In a recent poll of 2,000 American adults, well, that's your sample. Remember, sample sizes for proportions are very large. 62% of this sample said that owning a home is a very important part of the American dream. Okay, that's going to be P hat. That's the sample proportion, okay, of that 2,000. Perform a hypothesis test to determine whether it is reasonable to conclude that the percentage of all American adults who currently hold this opinion is higher than, it's greater than, 55%. Okay, so this is going to be your null. This population proportion is your null. Your alternative is going to be P is greater than 0.55. This is your sample proportion, okay? And there's your N. All right, using a 10% significance level. divide by 100, 0.10 is your alpha. All right, the only other value we need since we have P is we are going to need Q. Okay, well Q is 1 minus P, so 1 minus 0.55 is 0.45. There we go. All right, so we're testing to see, is this population proportion actually greater than 0.55%? Okay. All right, here we go. We're going to use both approaches. Well, regardless, we can delete this right here, by the way. Regardless of which approach we use, we still have to know our formulas, right? We still have to use those. So we've already found Q. Now we want to find sigma p hat, and we want to find z observed. Remember, this is our test statistic in case anybody asks. Okay, here we go. So we're going to have sigma p hat, which is going to be P times Q divided by N. So P times Q divided by N. We take the square root of that whole thing and take it out 4 decimal places. We get 0.0111. Now, if I find z observed, I'm going to have p hat minus p divided by sigma p hat. And I get 6.31. That is my z observed value. Okay. Now, we want both approaches. So we're going to take a p-value approach. Okay, so p-value approach, here we go. Calculate z observed from the above formula. We already did that. Then we're going to use normal CDF. Okay, we're going to use normal CDF using z observed. We don't have to multiply our answer by 2 because it is not a two-tailed test. And what we find from this normal CDF is our p-value. Okay, so here we go. Remember how to draw the picture for a p-value approach. We are looking at a right-tailed test. We're not doing regions anymore. And this is not the critical value when talking about the p-value. This is the observed. Okay, so what you're trying to do is find this area. This is your p-value that you're looking for. So you're going to do normal CDF, your lower bound 6.31, your upper bound is positive infinity 0,1. And if you forget that, it's right here. Okay, right-tailed test, z observed, positive infinity 0,1. Okay, it's right here. It tells you what to do with a left-tailed, tells you what to do with a two-tailed. Okay, this little sheet tells you everything you need to know. Okay, so here we go. All right, I'm going to go second vars down to normal CDF. My lower bound is 6.31. My upper bound is positive infinity 0 and 1. And, ooh, I get a really weird p-value. Okay, 1.40. That e to the negative 10th is times 10 to the negative 10th. That's an itty bitty 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 p-value. What does that mean? That means it is so tiny that if I went over 10 places to the left, what would that look like? That's essentially 0. Your p-value is essentially 0. Because think about this. I didn't even think when I wrote 6.31. 6.31 is actually way out here in the tail. So what we actually have, if I were to draw this accurately, is 6.31 is like way out here. And this is your p-value, which is basically nothing, basically 0. Okay, so that was my fault for just blindly drawing it, not thinking about it. Okay, so your p-value is basically 0 there, because if you round it to 4 decimal places, this is still going to come out to be 0. All right, now my alpha is 0.1. Okay, is 0.1 bigger than 0? Of course it is. Of course that's bigger than 0. Okay, this means it is significant enough. We are going to reject the null. That would be our decision, to reject the null. Okay, so let's keep going. Let's find the critical value. If we were to find the critical value approach, okay, what would happen with that? Well, sorry guys, I keep making it so you can't even see. Okay, critical value approach says find Z observed, already did. Find Z critical using alpha as the area and inverse norm. All right, so if I were to draw this, here we go. We have a right-tailed test. I don't know what my critical value is, but it better be positive. Now we have regions. We have a non-rejection and a rejection. And now this area is alpha. Remember, that's a little different than what we're used to. That area is alpha. Okay, so now we're going to do inverse norm. Our area is 0.10, comma 0, comma 1. Okay, we're going to go back to second bars, but we're going down to inverse norm. Our area is 0.1. Now, this is going to give us a negative, but we're going to make it positive because remember, it's actually everything to the left. So I would have had to put in 0.9 because it's calculating from here over. Okay, so 1.28 is what we're looking at as our critical value. All right, now our Z observed is 6.31. Z observed, okay, is going to be way over here, right? And in this case, that's definitely in the rejection region. So we are going to reject the null. Okay, either way we reject the null. So when we go up here to this box says, we can conclude that the percentage of all American adults who currently hold this opinion, okay, it's a drop-down box. You're going to click higher than 55%. That's what you're looking for because we rejected the null, which meant, in fact, the alternative is true. Okay, it is higher than 55. All right. Let's continue on here. We're going to finish this with the proportion. Okay, number 14. According to a Pew Research Center nationwide telephone survey of adults conducted between March 15th and April 24th of 2011, 55% of college graduates said that college education prepared them for a job. All right, here it cited the evidence. So this is going to be your P. I think that's the same P we had before. Okay. All right, suppose this result was true of all college graduates at that time. In a recent sample of 1850, there's our sample size, college graduates, 59% said that college education prepared them for a job. This is your P hat. It came out of this sample. That's your P hat, okay? Is there significant evidence at a 2% significance level, divide 2 by 100, 0.02, to conclude that the current percentage of all college graduates who will say that college education prepared them for a job is different from 55%. Well, what does that mean? Well, here's our null, that P is 0.55. Our alternative is what? Different from. That doesn't mean greater than, it doesn't mean less than, it means not equal to 0.55. When you see the word different, you know that means a two-tailed test. So that's what we're doing now. All right. Well, if our P is 0.55, you know we're also going to need a Q. 1 minus 0.55 is 0.45. Don't forget that Q is just 1 minus P. It's on that reference sheet if you forget. Okay, so not only do we need to actually come up with an answer to this hypothesis test, but it wants the Z observed, the p-value, and both critical values because it's a two-tailed test, so we're going to have a negative and a positive. Okay? All right, well, we know we're going to need sigma p hat. That's going to be P times Q divided by N. That gives us 0.01157. Okay? We know we're going to have a Z observed. That's going to be P hat minus P divided by 0.01157. That gives us a Z observed of 3.46. 3.46. All right. Can put this right up here. There we go. Okay, let's do a p-value approach first. All right, so remember, we're going to be using normal CDF. We're going to need a lower bound and we're going to need an upper bound. Okay, if it helps you to draw it, you can. Just remember, this is different than critical value. We no longer have regions. You have to be very, very careful here. So this Z observed becomes these little boundaries. Okay, there we go, a positive one and a negative one. So you can pick either region. Doesn't matter, you can pick either region for the p-value, okay? Because that's what these are. These are p-values. But pick one with either lower bound and upper bound or lower bound and upper bound, and then you can multiply it by 2 because we have 2 regions, okay? So here we go, normal CDF. Okay, I'm just gonna do this one over here. I'm gonna have 3.46 is my lower and infinity is my upper, 0 and 1. Or I could have had negative infinity is my lower and negative 3.46 is my upper. Whatever you wanna do. Okay, here we go. To clear this, I'm gonna do second vars, normal CDF, 3.46 lower, positive infinity upper. I get, oh, that little bitty tiny thing there. Okay, we gotta write it down. 2.70135 times 10 to the negative 4. Now, we can't just automatically assume this is 0 like the one before. This was a negative 10 on that one. A negative 4 is not really that tiny. If we scoot over 1, 2, 3, 4, that's actually 0.00027. Okay, that's not terrible. All right, now we're going to multiply by 2 since it's a two-tailed test. Okay, I just abbreviated because I'm getting lazy since it's a two-tailed test. Okay. All right, so if I do that and I round to 4 decimal places, I'm gonna get 0.0006. That is a little bitty p-value. So, you know, really these should have been way over here. Again, I kind of messed up our picture. All right, let's see how alpha shakes out compared to this. Alpha is 0.02. So is alpha larger than our p-value? Sure it is. Sure it is, larger than p-value. So this is significant enough to make us change our null. So we are going to reject the null. Okay. All right, let's squeeze in the critical value approach down here at the bottom. Okay. All right, so here's our critical value approach. Okay, we can make our little table here, our little picture. We're going to have two critical values, a positive and a negative. Here's our rejection regions shaded in. Now remember, we're going to have to take these are alpha, divide by 2. This gives me 0.01 on each one of those. All right, so I've already divided my alpha by 2. To get my critical value, I'm going to do inverse norm alpha, which is 0.01, I had to divide it by 2, comma 0, comma 1. Okay, so second bars, inverse norm, put in my area. Remember, I had to divide it by 2. I get negative 2.33. Okay, so I'm going to have a negative 2.33 and a positive 2.33. Now I take my z observed. Where does z observed fall in? Over here, 3.46. That's definitely the rejection region. So again, I'm going to reject my null. Reject my null. Okay. All right, so what does this little drop-down box up here talk about? Okay, this drop-down box says, we can conclude that the current percentage of all college graduates who say that college education prepared them for a job is, scratch through this, different from 55%. That's the drop-down box you're going to choose because we rejected the null, which means this is now the truth. Okay? All right, it's going to get faster, I promise. Those were the worst. Okay, hang in there. Here we go. We're looking at 15. We only have 18. 15. We do not have to do both versions here. So 15 says we have a random sample of 550 observations. It produced a sample proportion, so we know we're doing proportions, equal to this. Well, what does that mean? What symbol is a sample proportion? This is why I tell you have to know your symbols. Sample proportion is p hat. Find the critical and observed values of z. So all we have to do is the critical value approach. Thank goodness, right? Critical value approach. Okay. For the following test of hypotheses, using alpha equals 0.025. Here's our null, p equals 0.30. Here's our alternative, p is greater than 0.30. Greater than means a right-tailed test. I'm just being lazy. I'm going to put RTT, right-tailed test. Okay. Well, if p is 0.30, q is 1 minus p. So my q is 0.70. All right. Well, let's jump right in. We need sigma p hat. So we're going to take the square root of p times q over n. We're going to get 0.01954. Okay, now we need a z observed. We're going to have p hat minus p all over n. It's going to give us 4.09. That's our observed. Okay, let's draw ourselves a picture. Okay, we have a right-tailed test. This is our rejection region. This is our non-rejection region. We're going to have one critical value. It's going to be positive. This is our alpha. Okay, now we want to know, what is this critical value? Well, if you look at our steps on our little paper that tell us what to do to find your Z critical, you're going to do inverse norm, the alpha, comma 0, comma 1. Okay. Inverse norm, our alpha is 0.025, comma 0, comma norm, or comma 1. All right, now remember, we want the positive version of this critical value. So we're going to do 1.96. Okay, 1.96. That is our critical value. Okay. All right, so now let's see, where does that Z observed fall? So if 1.96 is the boundary between the two regions, Z observed is 4.09. It's way down here in the rejection region. So Z observed is in the rejection region. So we are going to reject the null. That's our conclusion. Okay, see, it's not so bad when you don't have to do both approaches. All right, number 16. Here we go. Okay, let that come into focus. There we are. Consider a null of P equals 0.70. Okay, so I know we're on proportion because I have a P and not a mu. Here's our alternative. Oh, not equal to. What kind of test is that? That's a two-tailed test. We have a random sample of 600 observations, produced a sample proportion. Sample proportions P hat equal to 0.68. Notice that for the last two, they gave us the sample proportion. They didn't give us a percentage, so I did not have to divide it by 100. I also have alpha, 0.01. Would you reject the null? Okay, well, I can pick. I can do critical value or I can do p-value. So it's really up to you what you would rather do. I think we ought to maybe do critical just because it's a lot quicker. But if you do want to see what the p-value approach would look like, you can go under content on my notes because I did do both approaches just so that you could see them both. All right, well, no matter what you do, you're still going to have to find sigma p hat. And you also are going to have to find q, which is 1 minus p. So 0.30. All right. Sigma p hat is going to be the square root of p times q over n. I worked that out. I came up with 0.01871. Okay. I'm going to find Z observed. That's going to be p hat minus p, remember that's from the null, all over sigma p hat. That gives me negative 1.0689. I don't know why I took it out so far, but there I did. Okay, that's my Z observed. Okay, I'm going to do critical value approach here, but again, you can do p-value if you'd rather, and both of them are on my content, on my notes. All right, we have a two-tailed test. We're going to have two critical values, a positive and a negative, with two rejection regions. Okay, for critical value approach, these are your alphas. And since I have two of them, I have to divide alpha by 2. That's going to give me an alpha of 0.005. Not an alpha, but a rejection region of 0.005. Okay. Now to get my Z criticals, I'm going to have inverse norm of 0.005, comma 0, comma 1. I've already divided alpha by 2, so I don't have to do that again. Okay, I'm going to go second bars, inverse norm, 0.005. I get negative 2.58. Okay, negative 2.58 and a positive 2.58. Okay, so now if I compare my Z observed, okay, where does negative 1.0689 fall? Okay, I know you guys aren't the best with your negative numbers on a number line, but it is right in here. It's in the non-rejection region. So Z observed is in the non-rejection region. We are going to fail to reject the null. And that's actually the drop down that you would choose. Fail to reject. Okay. All right, I know I'm going a little fast here, but I figure you guys are getting a little antsy to be done. That's why I just gave you this whole chapter 9 for 3 days, because I thought you could split it up, you know, if you wanted to. All right, here we go. Oh, I should have done a p-value approach on 16, because now I got to do critical value for 17. Oh, well. Okay, 17. A random sample of 480 observations produced a sample proportion equal, it's p hat, to 0.37. Find the critical and observed values for Z for the following test of hypotheses using alpha of 0.1. It's a big alpha. All right, so here's the null. Here's the alternative. Notice it's a not equal to or a different than. This is a two-tailed test. Okay, well shoot, I wish we had gotten to practice the two-tailed with the p-value, but that's okay. You can always go back and look at my notes. All right, wants the critical value approach, so that's what we're gonna do. Let's find Q, it's 1 minus P, so it's 0.7. Let's find sigma P hat, it's gonna be the square root of P times Q divided by N. That gives us 0.0209. Let's find Z observed, P hat minus P divided by sigma P hat. It's going to give us 3.35. Remember, that's also called your test statistic. Okay, here we go. We're going to make our little curve. We have a two-tailed test. Critical value approach says these are now regions. It also says that these rejection regions are equal to alpha. And since we have 2 of them, we're going to have to divide our alpha by 2. Each region is going to be 0.05. We need these critical values. Our Z criticals are going to be inverse norm with one of the regions. I've already divided it by 2, so I don't have to do it again. I'm going to put that in my calculator. I'm going to put 0.0501 and come up with negative 1.64. Okay. And I'm also going to make a positive one. So the left one is negative, the right one is positive. Make sure you notice that's how they word it a lot of times. Okay, now what are we going to do? Well, our Z observed is 3.35. The 3.35 is definitely over here in this rejection region. So Z observed is in the rejection region. We are going to reject the null. There we go. All right, we have one more. Can you believe it? I can't wait. Okay, last page, the very back. Okay, number 18. Okay, so according to a study, this one's tricky. That's why, I always save the best for last. According to a study, 11% of children in the U.S. lived with at least one grandparent. Somehow I got this all messed up. Just a minute. Okay. All right. Suppose that in a recent sample of 1580 children, so 1,580 is our N, 238 were found to be living with at least one grandparent. Well, that's interesting. At a 2% significance level, divide that by 100. Here's your alpha. Can you conclude that the proportion of all children in the U.S. who currently live with at least one grandparent is higher than 11%? Use both approaches. Okay, so we need a null, we need an alternative. That first sentence is usually your null. Here we go. According to a study, 11% of children in the U.S. lived with at least one grandparent in 2009. We're going to take that 11% and we are going to make it a decimal. There's our null. Our alternative is that it's higher than. Well, that's greater than 0.11. Greater than is a right-tailed test. Okay, let's make a Q. It's 1 minus P. Okay, we have our N, we have our alpha. What do we not have? We don't have P hat. We have this mysterious 238 number. Okay, remember, P hat is a sample proportion. It's a decimal. P hat is not 238. You are going to have to make a P hat. It's going to be 238 divided by 1580. That is your P hat. So that's the trick to this problem. You have to come up with your own P hat. So that ends up being 0.1506. Now you have all your information. Okay. Now, we are going to do both approaches, but first, no matter what, we are going to need sigma P hat. So that is the square root of P times Q over N. That's going to give us 0.007872. We're also going to need Z observed. That's going to be P hat. Remember, that number is what we just came up with. Minus P divided by sigma P hat. That gives us a Z observed of 5.158. Okay, there we go. All right, now we need to come up with our approaches. So we are going to first need to do a p-value approach. Okay, so remember, to find your p-value, you have to use normal CDF. And you have to use a lower bound and an upper bound, okay? Well, we want to be greater than 0.11. So guess what? What we're going to do, I shouldn't have said that. That is not your p-value approach. I just confused some of you. We're going to be using this, okay? So if we draw it, here's what we have, okay, for our p-value approach. This is your p-value, okay? This is your Z observed. So you are going to do, for your p-value, normal CDF. Your lower bound is 5.158. It is not this. Don't look at that, okay? The greater than just tells you that it's greater than, but it has nothing to do with 0.11. So we're going to take our lower bound of 5.158, our upper bound of infinity, comma 0, comma 1. Okay, that is going to give us, okay, normal CDF, lower bound of 5.158, upper bound of infinity, one of those itty bitty little numbers. Okay, now if it's a -4, a -3, a -2, go ahead and work it out and you'll get a decimal of some type. Anything from -5 to 6 to 7 to 8 to 9 and so on, just put 0. Just put 0. Your p-value is 0. This is so large, it's actually way out there. So your p-value is 0, okay? So alpha is 0.02. That's definitely larger than 0. So it is significant enough to reject the null. That would be your conclusion, reject the null. Now, it wants us to do it both ways, so let's look at critical value. Okay, so with critical value, we have regions. We're going to have a very clear rejection and non-rejection region. This is alpha. For your critical value, you're going to use inverse norm with this area, comma 0, comma 1. Put in inverse norm, our area 0.02, comma 0, comma 1, -2.05. That's good. Now we want a positive, so 2.05. We have a right-tailed test, so we want our z critical to be positive. All right, let's take our z observed. Where does that 5.158 fall? Down here in the rejection region, right? Z observed is in the rejection region. So we are still going to reject the null. Okay, we're still going to reject the null. All right, last but not least, I just want to tell you, I didn't put one of these questions on here, but it will have questions that give you N and P, and they'll ask you if the sample size is large enough. What they want you to do is multiply N times P and see if it's greater than 5. Multiply N times Q, see if it's greater than 5. That's what that means. I didn't think we needed to do one of those, but I wanted to remind you of that situation. And that, folks, finally brings us to the end of statistics. So that's all your material. I will get a test 4 study guide put together for you, as well as a video, and get that posted for next week. So enjoy the rest of your week and your weekend, and know that I miss you very, very much. Let me know if I can help you with anything. Bye-bye.